Hello everyone, welcome to the fourth lecture about system programming, a part of your favorite course of lectures. On this one we will be looking at signals and interrupts, what these things are, how they are working, how we can use them, and we will look at them at all levels as usual, starting from the hardware, then we continue into the kernel and then into the user space. Today we will follow this plan. We will look at the interrupts on the CPU, how they are working, what they are. Then we look at how they are being handled in the kernel, how they turn into signals into the kernel, at least some of them, and then how to work with signals in user space. First of all, I have a question for you. You're supposed to remember it from the previous lectures. What examples of processor interrupts you can recall from our previous lessons? Put the video on pause, think about it, and I will reveal the answer right now. We saw at least the following ones. First example would be hardware clock, which sends interrupts to the CPU, which in turn allows the CPU to rotate the tasks on the CPU cores. Then we also saw, for instance, page fault, which might happen on attempt to write into a copy on write page, or an attempt to access bad memory or protected memory, or page is not found in TLB or stuff like that. Then we also saw that it's possible to use an interrupt instruction for things like debugging and system calls. It is like a controllable interrupt. Interrupts are in general divided into two types, hardware and software. Hardware, we need to communicate with peripheral equipment in asynchronous mode. Something that is not a part of your computer, it's connected to it externally and the CPU wants to communicate with it. The kernel wants to communicate. And the software interrupts we need for out-of-order processing of exceptional situations like division by zero or a page fault or things like that. It's something which is, we can say, usually happens directly on the CPU. It's not coming from some other external hardware. Let's start with the hardware interrupts. Imagine that we have an I/O device. An SSD and HDD doesn't matter. It's connected to the system somehow, for instance via USB connection. It doesn't matter really. And then some program wants to read something from this device. What it will have to do, obviously, is firstly make a system call read, which will reach the kernel. In the kernel, it will go through some layers, like firstly through the virtual file system layers, so the request to read something actually understands which file system is, how to read anything from it, and so on. Then this turns into a more simple request like read from the specific device, specific bytes, starting from this and this much. So it will be sent to the driver, which can execute such operations, and then driver will send the request to the device somehow. Typically this would be through the bus on the motherboard. So the driver will put the request on the bus and the disk will read the request from the bus. This way the request is sent to the disk. Now we are facing the next challenge. How do we receive the response from the disk? Because the reading will not be instant, right? If it's HDD, for instance, reading can take like a millisecond. It's very long. So we have to find a way to receive the response much later, after we have sent the request. And there are multiple ways to do that, really. For instance, a naive approach would be that let's make our CPU core periodically go to the disk, like every, let's say, microsecond. Poke it and ask like, is my request finally ready? Is my request finally ready? Is my request finally ready? And as soon as the disk says yes, the CPU will read the response. The response will be in some sort of, I don't know, will also be exposed to the bus. Right? And then technically we executed the request and received the response. The negative side here is that we will have to make multiple requests to the disk. We will occupy the bus for this. It will be additional work for the CPU and for the disk controller as well. This is a lot of resources wasted. This is not a good solution, even if it works. And this gets worse when we realize that this will have to be done for every device, and there can be like really many devices. This approach doesn't scale, this polling thing. What we can try to do otherwise is instead of doing the pull, like with polling, when we try to pull the response from the disk, we could try to use a more reactive, like a push approach. So we firstly send request to the disk and then we continue doing other stuff. The CPU core is completely occupied with other things. It completely doesn't think about the disk at all. Eventually, when the operation on the disk is complete, the disk itself will notify the CPU core. It will send some sort of signal back to the CPU like, my operation is ready. You can come and read it. This would be convenient, right? It would be a request being sent to the disk, response being sent to the CPU. They don't need to ping each other all the time. This would be very efficient because it would be just two requests from the CPU. Firstly, we send read request to the disk, then we read the response from the disk. Very efficient and will scale very well. An interrupt begins with the device wanting to tell something to the processor. The device is connected to the motherboard via one of the input ports that in turn can be connected to the bus. The bus is this horizontal line that you can see on the slide. The bus connects the device to a special chip called Programmable Interrupt Controller, or PIC. And this is a hub for all the interrupts. To there, each device will send signals over the bus when it wants something from the kernel. The hub will collect all the signals, arrange them by priority, and forward them to the CPU core for handling. And then CPU core will handle them one by one. It cannot handle them more than one in parallel. Let's consider an example. So imagine we have a device, some sort of disk. It wants to tell something to the CPU, so it will send the signal to the PIC, Programmable Interrupt Controller. The CPU, let's imagine right now, cannot handle the interrupt, so the PIC will save the interrupt in some sort of queue. And then another device also wants some attention from the CPU core, so it will send another signal to the PIC, which will also be saved there. And those signals will keep being collected into the queue on the PIC device. And then eventually the CPU is signaling that it is able to handle the interrupts, finally. An example why CPU was unable to handle them before, maybe it was handling some other interrupt before that. Maybe it was in some sort of context which cannot be interrupted for whatever reason, like the kernel just disabled the interrupt handling, right? For whatever was the reason, it was unable to handle them before, now it is able to, so it will start receiving those interrupts from the PIC device. It will handle them one by one. Each time when it receives the next interrupt, it will have to know from which device it was when it appeared, right? Because it was sent some time ago. CPU already doesn't know from where it came from. So the PIC for that will help the CPU by exposing the number of the device which sent the original interrupt in a special register. And then the CPU can read it and understand this. This interrupt was from device number 1. Then it's handling it, cannot take new ones for now. Then it is handled, it will take the second one, will handle it as well. We will see that this is from device number 2. In the binary system, it's going to be written as 10. Then it is also being handled, and then it's finished, and then it gets repeated as new interrupts are arriving. Software interrupts, unlike hardware interrupts, are generated by the processor itself. Technically, we can say like literally everything is hardware, right? Because the CPU is also hardware. But the clear distinguishment, I would say, would be that software interrupts are appearing directly from the code which the processor is executing. And the hardware interrupts are coming from other devices, not from the CPU itself. This would be the criteria which we could use to say what is hardware and what is software interrupt. And the software interrupts are divided further into two more categories: errors or exceptions, and also traps. Errors are kind of interrupts that are not supposed to happen, and when they do happen, they require to handle some exceptional situation, hence they are called exceptions. And if it can be handled, then it is supposed to be fixed and the instruction will get executed again. If it cannot be fixed, then the process cannot continue and then it probably will be killed by the kernel. Some typical examples would be, for instance, when the CPU is trying to make a write into a page marked as copy on write. So it has to be copied before writing into it. This will trigger an interrupt. The kernel will handle this case, like copy the page, change the mapping of the virtual addresses in the affected CPU, in the affected processes, and then it will execute the write. Right? Yeah, so the write, which caused copy on write interrupt, it still has to be executed. This is why this instruction will be executed second time. And this is what we can say probably is the biggest difference with traps. Exceptions, they will be retried if they were handled gracefully. While traps, they will not be retried. Traps are not errors or exceptions. Trap is like, it's a graceful interrupt, which is purposefully emitted. It's not like something that is happening unexpectedly. It's something we do on purpose, for instance, to enter the kernel context. And this is how our working system calls, as we saw in the previous lectures, or debugging instructions are also working like this. Let's get back to the interrupt handling. Assume that it has happened, so interrupt is here. Software or hardware, it doesn't matter at this point. It should be processed somehow by the kernel. Which means kernel should invoke a function to handle this interrupt. And there is a couple of questions, how can we even do this at all? Like, similar to how I was asking you how system calls can be executed in the kernel. Here the idea is the same. There is something we need to execute in the kernel because something happened in the hardware. And firstly, there can be many things happening in the hardware, right? More than one. Different kinds of exceptions, errors, traps, and they are all divided into different types of things happening, like copy on write, TLB error, page fault, whatever else. Right? And do we like create one function which will be handling them all, or we create separate functions for every reason? And whatever we do, how do we find this one function from the hardware directly? So hardware could invoke it in the kernel context. And then another question is that probably the CPU right now, when interrupt happened, was doing something, right? It was executing the code. Probably it was some user space code. And we need to stop this code being executed, handle our interrupt, and then continue executing the user code, user task. And the task should not even notice that it was interrupted. So how do we even do this? How do we interrupt current task in a way that it can be restored later? I suggest you think about it, put the video on pause, and I will reveal the answer right now. What we can do is that the context of the task that is being executed right now, we can simply save into the main memory somewhere, right? Because the context of a task is not so big. If you think about it, what it really is, it's stack. Stack is a single number. It's a pointer, like it's an address of the top of the stack. That's all we need to know. So we can save this one number somewhere, instruction pointer, which was saying which instruction was being executed in the section text of the task. Yeah, it's also one number, which we can also save somewhere cheap. A bunch of other numbers like registers, which are used to pass arguments into functions, special purpose registers of any other sorts. Basically, context of any task is just a bunch of numbers, which we can simply save somewhere. It's not expensive. And then we need to find the function to handle the interrupt. What we can try to think of as like, let's have a special register. Again, you don't know how to pass something between the hardware and software, create a special register for it. Here we will do exactly that. We will create a special register where we will store pointer at one function, handling all the interrupts, or we can say, for instance, we have an array of functions and we will store in a special register beginning of this array, address of the beginning of this array. And then the CPU core will just pick the needed function and invoke it. This should be very simple to do. And this is what is really happening in the hardware and in the kernel. Before searching and invoking the necessary function, the context of the interrupted process will be saved somewhere. The context is always fully described by a set of registers, depending on the processor architecture, but anyway, it's just a bunch of numbers. We will save them into the main memory, into some pre-allocated memory, which the kernel will pre-allocate for every CPU core at startup. And we will just use this memory. We will not even have to allocate it. It's already allocated. We just copy stuff into it. And then the context is saved. All good. And then after it is done, the interrupt handler should be located and invoked. For this purpose, what is happening in hardware and the kernel is that there is a special entity called interrupt descriptor table. It's a complex name for a very simple thing. It's just an array of functions. Array of addresses pointing to C functions. And there are just 256 entities in this array. This array is plainly stored in the main memory, and there is a special register IDTR where the beginning of this array is saved, address of this array. And when the interrupt needs to be handled, the CPU will take address of the beginning of this array, use number of the interrupt as an index in this array, and will just invoke the function by that index. It's very simple. This table, EDT having 256 values in it, handlers, addresses of the handlers, it's having some numbers reserved by the hardware, so the kernel cannot change them to any other purpose. For instance, debugging would be interrupt number 3, or page fault would be number 14, or the zero division will be number 0, the first handler in the array, or some other very hardware specific things. And some handlers, some items in this array are free to use by the kernel as the kernel wishes. For instance, the interrupt number 228 will be used by the Linux kernel for system calls. But this is only by the Linux kernel. Some other kernels can choose another interrupt, or even not interrupt, not this way of interrupts at all, or whatever. Right? This is not hardware thing. It's just something that the kernel decided to do with a free entry in the IDT table. And after the handling of the interrupt, all the context saved in this special memory by this one CPU core, it will be restored back, so all the values of the registers will be set as they were before the interrupt, and then the core will continue executing the previous task, unless the kernel decided to remove this task from execution, of course. Some interrupts, some numbers of those interrupts you can find, and they obviously will be depending on the specific hardware, and the ones defined by the kernel will depend obviously on the kernel itself, but we can be sure that most, or if not all, hardware and software will have the following interrupts, like division by the 0, or breakpoint, or invalid instruction, page fault, and so on. Right? And again, regarding Linux, if we would speak about Linux, then there is number 128, which is used for system calls, and probably many others. This was all about the low-level part of interrupt handling for one processor, where the handlers are stored, how they are looked up. We just saw all this. For multiprocessor systems, as I mentioned, it's a bit more complicated. There is an APIC, Advanced Programmable Interrupt Controller, and there are multiple CPUs. I don't know, to be honest, how do they handle interrupts in the kernel. Let's say if it would be running on Linux, is it then able to run them in parallel, the handlers, or not? But this is advanced topic which you can look up separately if you are getting interested in this. We are moving on now to the software part of the interrupt handling, which is located in the kernel. In the kernel terminology, the interrupts are not called just interrupts. They're called interrupt requests, which actually is making a lot of sense if you think about it, because interrupts, we do not handle them in the kernel right away when they come. Interrupt is not causing an interrupt instantly, right? They are being stashed into the PIC device, Programmable Interrupt Controller, and only are handled later. So technically every interrupt is saved as a request in the peak and then later is handled by the kernel, which means interrupts are actually interrupt requests, which might be, I don't know, ignored, or if they are getting duplicated from the same device, can be merged into one interrupt request and so on. And then the handling code, like the handler function of the interrupt, is called in the kernel interrupt service routine, or ISR. And those terms, IRQ and ISR, probably not very necessary to remember them by heart and always keep them in mind, because you very rarely will see them. But sometimes you can see them in some literature. So it makes sense to know about those things existing. You don't need to always keep them in your mind, but it might help you in the future if you know, if you heard those terms before. Let's say it like this. The handlers ISR, they are executed inside the kernel process, and if there are multiple interrupts incoming, they will be handled one by one. As we have seen, the peak controller will take care of that. Because of this sequential behavior, the kernel will try to handle the interrupts very quickly to ensure that the handler function does not block any global resources and new interrupts can continue being handled. For example, if we speak about, for instance, an interrupt from a keyboard, like you press a button on a keyboard, this will have to trigger an interrupt in the kernel, because the kernel will have to understand which button was pressed and deliver it to the corresponding user space process. And then the kernel cannot handle the complete logic of this interrupt at once just in the ISR function. It is just not possible, because it will take too long time. It will probably not take like a millisecond, but it will likely take hundreds of microseconds, maybe tens of microseconds, but it is still very long. It would be way too long because other devices will be unable to deliver interrupts, to deliver their events to the kernel while we are just handling an event from the keyboard, right? This doesn't make much sense. This will not scale. In a high load, like, yeah, keyboard is not super frequently happening compared to the frequency of the processor, right? Because we are pressing it literally with our hands. We cannot do it too frequently, but imagine a network card which is receiving network packets at a speed like gigabytes per second. This will create probably a lot of interrupts, and we should be handling them as fast as we possibly can to unlock the next interrupts. What we have then is a more general issue that some interrupts, they require heavy handling, like reading a lot of data from some device or forwarding this data into the user space, right? We cannot handle all of this right when the interrupt happens, because then we will block handling of the next interrupts, and then the whole system will be slow. It will be reacting to events from devices not fast enough, probably. And this is why in the kernel the handling of the interrupts is divided into two parts, called bottom half and top half. Top half is the part of the interrupt service routine which is being processed exactly when the interrupt is coming into the kernel. So this is literally what is invoked when the peak delivers interrupt to the CPU core. And during execution of the top half of the handler, new interrupts cannot be coming. And top half will have to be very lightweight and fast. It will have to do things like find the reason of the interrupt at first, then save urgent data, whichever will be lost after this function returns, unblock the new interrupts, right? And then, if this is required, schedule background handling of the heavy part of the interrupt, which will require some work, which doesn't need to block the interrupt handling. For instance, if we speak about networking, top half could say, for instance, in some global context, that this device saved memory of the network packet into I don't know, on the bus or somewhere in the main memory it's already saved. And then we will schedule handling of this thing in some sort of thread pool. And then top half returns and new interrupts are being processed. And then later this thread pool will notice that there is a task posted by top half that we need to read some network packet from the main memory and forward it to the user space. And this will be handled outside of the interrupt context and can be being handled in parallel by multiple threads, multiple tasks. And this way of handling things with top half and bottom half, like two parts of handling one thing, it's not just a kernel specific design pattern, I would say. This is something you can also do in user space, in business applications. For instance, again, imagine networking. It's just the simplest case for high load, high frequency things. Imagine that we have networking application where we have a thread pool which is reading from multiple sockets some data. It will be reading the data from sockets. I/O can be a pretty heavy thing because it involves system calls, can be slow. And then it's reading this data from the sockets, and then maybe it's decrypting it because it's encrypted with SSL, and then it's validating all the requests and allocating memory for our messages and so on. And then we want to handle them. Handling may be even taking longer time, right? Maybe those requests, they need to make some sub requests later, but they need to do some heavy CPU work, I don't know, some heavy logic work. It cannot be handled really in the I/O threads, right? Because then we will stop handling I/O if we receive too many requests and they all take their I/O threads out for doing the business logic work. This would not be scaling again. So what typically happens in the applications is that there is one thread pool for handling I/O and another thread pool for handling business logic requests. And the I/O threads, they will create requests and postpone their handling to be done by the second thread pool. So while one thread pool is handling business logic, the other thread pool will be able to continue handling I/O. This scales relatively well, I would say. You will see this in many high-load applications done this way. Registration of a top half handler is done by the eRequest thread.irq function. It takes several interesting arguments. Firstly, it will take number of the interrupt line to catch the interrupts at. So it's like the pin number on the peak device. Then it will take the handler function itself, the top half handler. Then it will take some internal flags, like should the interrupts be blocked while this function is being executed or whatever else. Then it will take arbitrary data used by the handler and passed unchanged into the handler itself. Like some sort of context for the function. This is just the way to do it in C. If this would be C++, for instance, that those arguments probably would not be needed. We could create a lambda function as the handler which needed data captured inside it, but in C we have to pass it separate. Let's have a look at a real example, it's a very simple example which shows the idea without confusing it too much, I hope. And this is timer handling. This is interrupt. This is the handler which handles interrupts from the RTC device, which we saw on the first lectures somewhere. It registers RTC interrupt function as a handler of each interrupt happening by the timer. Inside this function, the kernel will update the clock counters, which will in turn later be turned into monotonic clock counters and then real-time clock and all this. But this is the basic monotonically growing counter increased every time when the timer interrupts the CPU. And this event doesn't even have bottom half because it's very simple, as you can see. And we can see here a reference to our previous lectures again. The scheduler wake up. As you remember, the threads, the tasks in the kernel, they are rotated on the CPU cores with a certain period. Like when one thread was working too long, then it will be removed from the CPU core and another thread will be placed on it and will get executed. And this way they rotate all the time. The system looks like it's working in parallel, but actually it's just switching the threads very frequently. This is where it happens. Every time when we receive an interrupt from the timer, the kernel will recheck if the current thread on the CPU core still needs to continue execution or it should be removed from it. It is possible to get a list of the interrupt handlers registered in the system. You can do it in user space even. For instance, for some sort of monitoring or analysis of the performance or whatever, like why is your system is too slow, is being interrupted too much, or some sort of device sending too many interrupts or whatever. And this list you can access via the procs interrupts pseudo file in the procs file system. As you remember, procs file system, it's all the files in it and directories are fake. They are not stored on disk. This is just API into the kernel directly, which looks like files, but it's not file. It's file-like API. And for each IRQ number, you will see here how many times its handler was invoked. Shows an optional text description and on which CPU cores it was being handled how many times. For instance, you can see here the timer interrupts, local timer interrupts, or at least it was when I was measuring it on my system. You can obviously have different names in your system. It all depends on the hardware, on the software, on the kernel, right? And we can also see here the interesting TLB shutdown interrupt. This is happening when TLB is cleared out because of some sort of collision, conflict, or whatever. This is a bad interrupt. If you see this one growing too much, it's bad. It means you are doing something wrong with the memory. This is hitting your performance. So you can use it for some sort of very low level performance analysis. So the top half can postpone not urgent work via the bottom half. And there are several solutions in the kernel how to do that exactly. So these thread pools that I mentioned before for bottom half. The kernel has 3 ways to handle them: soft IRQ, tasklet, and work queue. Soft IRQ is the oldest and fastest way in the kernel to postpone the work, any sort of work. Consists of static array with 32 items, 1 per interrupt line number. And when an interrupt based on soft IRQ wants to postpone some work, it will set a flag in its item in this array. And the flagged interrupts have their bottom halves executed in the background. In special case soft IRQ worker threads. This is literally like I was describing some sort of abstract bottom half handling. Top half records from which device the work came, it saves a global flag, and then bottom half thread pool will notice this flag and go talk with this device separately or with memory or whatever. This is probably the simplest and most trivial way how it can be handled. Tasklet is another API also for soft IRQ that supposedly simplifies the interface a little bit. I have never worked with it, but this is what I was reading. And work queue is just a generic way to postpone work in the kernel again. Can be used not only for the interrupts. So this is literally like abstract thread pool, this work queue thing. And software interrupts are usually simpler and faster than hardware interrupts. Are always processed by the kernel itself, not by the drivers or other third-party modules. And before we continue further, beyond the topic of just the interrupts, I will have some control questions for you that you should be able to answer easy after what you have heard so far. So firstly, what 2 types of interrupts you know and when are they used? Put the video on pause and try to remember what we just talked about. I will reveal the answer right now. Hardware and software. Hardware we use for asynchronous work with periphery devices, and the software interrupts we use to handle exceptional situations happening in the code, in the machine code executed by the CPU core. Another question: where are hardware interrupts stored before they are processed by the CPU? Put the video on pause and think, and I will reveal the answer now. They are stored in the PIC or APIC, Programmable Interrupt Controller. Only from there, the interrupts are forwarded to the CPU one by one. In the PIC, they are stored in a queue and are forwarded one by one because CPU cannot handle them all in parallel and it might be unable to handle any of them right now if it's busy with some uninterruptible work. Another question: where and how the kernel finds an interrupt handler when an interrupt is finally ready to be handled. Try to think, put the video on pause. And I am revealing the answer now. From IDT, interrupt descriptor table, it is stored in the main memory and its beginning is saved in the IDTR register, which the CPU knows about. It will take the address stored there as the beginning of the array, number of the interrupt as an index in the array, and then it finds the handler. User space has no idea about processor interrupts and it cannot neither detect nor handle them in any way, neither directly nor indirectly. It's just not possible. But some of those interrupts might be delivered to user space in a changed form of so-called signals, which serve the same purpose as the interrupts in the kernel, to deliver asynchronously some sort of events into user space when it makes sense for user space to want to handle them. Although the signals, we can say, are firstly a bit more specific than interrupts, because they target certain processes or threads, not the whole system. And secondly, we can also say they are more generic, because they can not only be used for projecting interrupts into the user space. They can also be purely initiated by user space, be sent by one process into another process, by one thread to another thread. They can also be used for things completely unrelated to the hardware at all. And also, by the way, they can also be used to project the interrupts into user space. That's like a side effect. And not all interrupts will get translated into the signals for user space, but some of them will be, and we can actually handle some of them in a way. Processing is done almost the same way as in the case of processor interrupts. When a signal is delivered to a process, the kernel will save the process context consisting of registers, and they will execute the handler function if there is one set at all. On the same or on a separate stack, it depends how you configure it. And there are a lot of signals, about 30. The exact count will depend on the operating system that you use and on the version of the system. And the list will usually be available at least on Linux in the documentation man7 signal or just man signal. And there you probably will find the complete list of signals on your system. And each signal will have a number, which is indicated in the code by constants with the sig prefix, and it's available in the file signal.h. Sigabort, sigalarm, sigint, sigsev, and some others. Some signals are not initiated by the kernel, such as sigint, which is usually sent by a parent process to the child processes when in the terminal you press Ctrl-C. Or sigalarm, it's a signal which is sent to a process by a process to itself with a delay, for example, to interrupt a too long system call. Most of the other signals are sent by the kernel as user space representation of critical hardware interrupts, like sigsev. The kernel will send to you when you get a segmentation fault, like page fault or whatever other memory issue, or sigfpe signal you will receive if you divide by 0, or sigtrap. It will be a breakpoint when it's encountered by the execution, or ptrace system call is in progress. And the process is usually free to handle the signals either using default behavior, or that usually leads to termination, or you can set your own handler for each signal as you wish, except for two signals which cannot be handled or interrupted. It's sigkill or sigstop. They will be working out of your control. There are two ways how to set a signal handler for a certain signal. The first one is old and it works differently depending on the operating system, on its version, and the version of the standard library. But it is very simple looking, and it's convenient for us to use as an example, at first at least, until we get slightly more advanced. In the real life, this method is used very rarely, so the fact that we're going to use it now does not mean you should use it later. We use it as a starter, but we will leave it when we get to more advanced things. This function is taking a signal number and the handler function, which will return also the previous handler function. So signal, it's like get and set. It will return the previous handler function. You can see it here. It returns the previous one, and you set the new one. So it's get and set. This way you can set a new function, handle some sort of signals, and then send the old one back, whatever it was, if you saved it as the result of signal. Function which is going to be handling the signals, it should take one argument integer, which will be the signal number. This way you can, for instance, use one handler function for multiple signals and determine which signal is received by just looking at the value in this argument. So let's consider an example. Here I set a handler for sig int, sig user1, and sig user2. Now at the control C, or at a custom signal sent through the kill function in the command line, I will be printing messages like I just caught sigint or user1 or user2, or I caught something unknown and then I exit in this handler function, which I set for all three signals at once. Right, let's compile and run this code. I see whatever my PID, and then I press Ctrl C and I receive sigint. Or then in another terminal, I'm sending user1 signal to my process by the PID. And I see that it was received. And then I send another signal and it was also received. And my function understood which signal is what. And then I send the final signal sigterm, or I think kill is sending sigterm by default, so this will just terminate my process. I did not set a handler for sigterm, so by default it terminated my process. I did not print this message. It was printed by the bash. My code did not handle this signal. So why signal is really looking simple, right? It's very hard to get it wrong, it seems. But there are a few problems with this function anyway, which make it unfortunately hardly usable. First of all, the signal handler was reset to default, at least previously, in early implementations of this function on each delivered signal. So it means you receive signal, and in the beginning of your signal handler, you must set the handler again. And if another signal comes at the same moment, like just after your handler started, but before you reset it back, this signal will be missed. This is like literally a bug. This is a very bad thing. Secondly, the behavior of signal is simply undefined in multi-threaded program. About undefined behavior, the thing is, it doesn't mean it's going to break. It just means that behavior is unpredictable, it's undocumented. So on one system it might work one way, on another system it might work another way. This is not documented in the standard and in any way, so we cannot rely on this behavior, even if we see that in our setup it's working okay. Technically, if we have a multi-threaded app, we just cannot know how signal works. Also, it does not allow to block a signal. It's not the same thing as ignoring a signal. You can ignore a signal. There is a special handler for the signal function which will literally just ignore everything. But blocking a signal means that when a signal comes, it is blocked, like stashed, in some sort of PIC, programmable interrupt controller, but in software. And when you unblock the signal, it will be delivered. So you like pause signal delivery. You don't ignore signals. This is a very different thing than ignoring. And signal function doesn't allow that, and sometimes it's needed. Because of this, the following example on the slide will work incorrectly. In this example, I want my process to wait for sig user1 until it is received, and then I want to finish. This is a very simple task, right? I also added some prints, so we will see what is happening. And in addition to this trivial logic, I also added invocation of interrupt function. This function will simulate like if my thread was put on pause by the operating system for whatever reason. I cannot guarantee, like if I wouldn't have this call, then it would be hard to reproduce the bug. But with this call, it doesn't change the logic, and yet it will help me to reproduce the bug. So let's see what is happening. I compile it, I run, I see I install the handler, then I deliver a signal, I receive it, and then I press enter to leave this interrupt call, and then without even entering the loop, I print finish and all is okay, right? No bug. Another case how it can work. I start this program again. I see that handler is installed. I press enter. I am in the loop right now, right here, before waiting for signal is started. Then I send the signal. It is received. You see? And then I start waiting for signal. Signal is received, but I will continue waiting for it again. For a second one. If second one never comes, then I will be blocked forever in this process until it is killed or second signal comes. This is not good. This is a bug which cannot be fixed with the signal function at all. I can press enter any number of times that I want, but I need another signal for this to get unblocked. This time I just kill it with sigterm. There are also problems which are common no matter how you handle the signals. Like when exactly is the process interrupted for signal processing. It can be interrupted literally at any moment. For instance, a process could be inside a long blocking system call. And if signal comes during that moment, you technically might receive an error from that system call with error code set to a special value inter. It means error interrupted. Yeah, you technically should be able to handle this error. It should be handled in your code, which almost never I see in low-level code. So many programs have this bug actually, if they want to deal in any way with signals. And another even like this is easy. You just retry usually. This is easy to fix. But the more serious issue, which is causing most of the headache, is that signal can interrupt a function working with some global state, for example, with the heap. And this is a big deal because interrupt can happen in a moment when you started changing the globally visible state. It is currently in some sort of inconsistent state, which should not be visible anywhere. And now you interrupt it, and the interrupt handler, you try to access this global state again, and you will observe it in an invalid state. Even if it is protected with mutex and everything, you still will either like literally deadlock or like very simple example. Imagine you have a globally visible state which is protected with the mutex. You lock it and then interrupt happens. Signal. In the interrupt handler, you try to access the global state again. You try to lock the mutex again and you deadlock because this interrupt was handled by the thread which already has the mutex. Right, those kind of races, data corruptions, and any sort of nasty things can very easily happen with signal handling when you are not careful. In the case of a function that uses global variables or global state of any sort, the problem is it's easier to show on an example probably. For instance, take simple functions like malloc, free, printf, scanf. They all use global variables actually. You might not be aware of that. They don't look like they use anything global, but they do use. Malloc, it uses the heap. Heap is global, it's per process. It's literally a data structure storing some memory blocks, which you can get from any thread. Where do you get it from, you think? From a global state. And because of having to be thread safe, the heap also has mutex locks. And printf and scanf, for instance, they use globally visible file descriptors, numbers 0 and 1, right? They also might be using some sort of thread local buffer in which they will be formatting their strings, right? Some functions which you never think as having some sort of global non-atomic state can actually have it. And if you don't know about this and you're not careful enough, and signal interrupt will happen during one of these special complex functions, and then they are called again during the interrupt handling, you will get some sort of undefined behavior. If you are lucky, it will work. If you are unlucky, you will get a crash, you will get data corruption, invalid instruction, or any other sort of nasty error. Let's consider an example. So I have here program which is installing SyncUser1 handler, and this handler will try to use the heap. it will do like malloc and free 10 times in a row and then leave. This looks valid, right? This code should be okay. Also, my main program, like outside of the signal handling, will just infinitely do this malloc free, malloc free, malloc free all the time. So it will always do something inside the heap. It is also valid. This program can technically, without any signals, run completely okay as long as it until we interrupt it, essentially. But with the signals, we can get into a situation when this function was somewhere inside malloc or inside free, and at the same time signal comes and also tries to do the same. So we call malloc while being already inside malloc in the same thread. This can break very nasty. Let's look. So I started sending sig user1 signal very frequently all the time, non-stop. And very frequently, very fast, I got the invalid instruction crash. So I received another signal, not sig user1, but another signal which told me that I tried to execute a legal instruction. So apparently I corrupted stack or I corrupted the heap in some way that everything broke. Code is correct logically, but factually I tried to call malloc inside malloc and this is where it got me. In this case, I'm also using printf inside the signal, as you can see. It is technically also illegal, but I'm doing it anyway for simplicity. All this means, what you see on the slide, is that most of the functions, most of the untrivial functions you just cannot use inside signal handlers. It is just not possible. The ones that you implement yourself, you have to take care of it. If you want to use them inside signal handlers, that they do not try to access any sort of global states. And when it comes to the standard library functions like malloc, printf, or whatever, technically you don't know which of them are safe or not because it's not written in their name, right? But luckily, at least on Linux, you can look up the list of signal safe functions. I think you will see them in the documentation of signals like this man7 signal or man signal. There should be somewhere literally a list of officially the signal safe functions which are allowed to be invoked inside signal handlers. For example, most of the pure system calls, they can be invoked inside signal handlers, like writing into a file, opening a socket, connecting somewhere. This is just mostly pure system calls, so they can be executed inside the signal handler. You can also use them to print stuff to disk or to the console. Without printf, you can still do it. As you remember, printf is just write inside. You can do it directly, then you have access to the console. Right, so technically you can do some untrivial things in the signal handlers, but to get it completely right will be very tricky. From what I have observed in practice is that usually people don't care about this. Most of the signals, they are crashes, and they are usually happening in user code, not in some library code. Which means normally it is not too bad if you use the heap, for instance, in the signal handler. It is very unlikely that you got crashed because of the heap being broken. So most of the time it will work. When you do get a crash because of the heap being broken and you try to use it in the signal handler and you get a second crash, then it will be very bad and very hard to debug, but it's very rare. So I don't know if you want to sacrifice simplicity of the code for handling this special case. People usually do not, whether you like it or not. Signals can not only be caught, there is also API to send them. As I have already said, processes can literally just send signals to each other. Signals do not have to originate from the kernel. For instance, when you press Ctrl+C, this is sent not by the kernel. It's sent by one process to other processes. I have already used one of these functions for sending signals, function kill. Terminal's kill command is actually just calling this function. It's a wrapper around it. It takes process ID, which will be the process to which you want to send the signal, and then the signal number. On the contrary, with the name, which is named kill, it does not have to be seek kill. You can send completely non-fatal signals to other processes using kill function. It's just the name is very strange, confusing. There is also function raise, which will send signal to itself. It is almost like kill, if you would call kill with your own PID. Right, except the difference is that, at least from what I have observed, is that raise will try to send the signal exactly to the thread which called raise. Signals can also be targeted to specific threads, not the whole process, and raise allows you to send signal to your current thread, which kill I think cannot do, but this you would have to double check if you ever want to use it in some logic. Better not rely on just the words, it's always easy to set up an experiment to double check this. Also there is function pause, which we already used a few times in examples. It will stop the current thread until any signal is received at all. So it's like wait for signal. And the function alarm is going to send to your process a sig alarm signal after the given number of seconds. Which is probably, maybe I don't know something, but right now it seems to me like the most useless function among the ones on the slide. Because you cannot control, I think, to which thread it is going to be sent, and the granularity is seconds. Well, usually you need at least milliseconds granularity in your code for any sort of timeouts. And if it was intended to be used together with blocking system calls, then right now it also doesn't make much sense, because most of the system calls which were blocking before, people now use in asynchronous mode, like asynchronous I/O is the most typical one. Very rarely you will try to work with sockets using blocking send and receive calls. You will usually use non-blocking sockets, asynchronous I/O. All the timeouts will be built on top of that in user space. So probably alarm is some sort of archaic old thing, but I don't know. If you are curious, you can probably Google it. Sometimes you need to block a signal, meaning that capturing it and saving it for later processing, not ignoring it. Ignoring and blocking are not the same thing. Typically this will happen when a low-level library wants to do something that cannot be interrupted by signals. But also we do not want to lose the signals if they were sent to us. Like, for instance, you want to work with some global resources in a way that it just cannot be interrupted by signals, because interrupt handler would like to use this global state. Then you can just choose not to handle the interrupts at all. You can just, the signals, you can just block them temporarily. And then your global state will be protected, right? And for this we use the function sigproc mask. It helps to achieve that. It can block and unblock signals for the current thread. It is important that only for the current thread. This is not going to be process-wide thing. The signal handlers, like when you call function signal, it's going to be process-wide. But the signal block mask, it's thread local. Each thread can have different signal mask. So some threads might be unable to receive certain signals right now, they will be blocked. Some other threads will be able to, and they can receive. It also means that if you want your global state of any sort to be protected from signals in the whole process, that it might be impossible to do really, because you would have to coordinate all the threads to do that together. So I would say the most beneficial case is when you just don't want your one thread to enter the same global state twice. Firstly in the normal context and then in the signal processor context. But protecting global state process-wide with this thing is, I think it's impossible really. It's too hard to achieve. This also means that when your process receives a signal, like not thread receives the signal, but the whole process receives a signal, then it will give this signal for processing to any thread which does not have the signal blocked. If all the threads will have the signal blocked, then it will stay blocked, will not be delivered anywhere until some thread will unblock it. And this is the arguments that it is taking. It is firstly taking the action what to do, like block a certain signal or unblock them, or set complete signal mask without blocking or unblocking individual signals. You can imagine that this signal mask is literally a bit mask, and you can decide if you want to set or remove individual bits in this mask, or you want to set the whole mask as a single big value. So this is what the how argument is doing. Then the set, first one, it's what to apply with the how action. For instance, if you say sig block, then the signals listed in the set will be blocked, in addition to the ones which were already blocked. If you say unblock, then they will be removed from the thread signal mask. If you say set mask, then this whole set is just assigned to the thread. And the old set is an out argument which will, where the kernel will place the current signal mask of the thread before the new one is applied. So it's again the sig proc mask function is like get and set. It will get you the old mask in this out argument and will assign the new mask in this input argument. And what is sig set type? It's, as I said, it's a bit mask, but you don't know what is it internally. Is it like int 32, 64, 16? I don't know. Maybe it's multiple. It's bigger than int 64. We have no idea. It's just some sort of sig set underscore t. To work with it, you need helper functions. You cannot set or remove those bits directly. And the helper functions are pretty much self-explanatory, I would say. So sig empty set, you can use it to initialize the set as just empty, like completely zeros. Fill set, like set all the bits in the mask, all of them to ones. Or sig add set, you set bit for the given signal. Del set, remove bit for the given signal. And sig is member, you can check if a signal is present in the mask. So you have pretty much all the possible getter setters that you can need in theory in your code. And another system call is sig pending. It's just a getter which will return you as an output parameter which signals have already arrived and they are pending for processing. So they are blocked in your current thread, but they are already waiting to get unblocked. And as soon as you unblock them, they will be handled. Let's try to write an example. So in here I set a handler for sig int here and block this signal until something is entered from the keyboard. So I do empty set, I add sig int to this empty set, so it's just this one signal in there, and I block it. Currently my thread cannot receive sig int. All the received sig ints will be just blocked, pending until I unblock them. Then I want to enter something from the keyboard. And then I will check if my signal arrived and it's pending for handling. I will check it by getting the whole mask of pending signals, and then I will check if sig int is there. And then I will unblock it, and I will see if it will be delivered as soon as I unblock it. I will also try here an experiment by sending multiple sig int signals. And I want to see what happens. Are they going to be received all 4 of them? Like I will be sending 4 signals. I want to check if all 4 of them will be delivered after unblocking or just one. So basically, is there like really a queue of signals? Or the same signals, they get merged into one and delivered as one when unblocked. Let's run this code. We start by blocking sigint, then I press Ctrl C 4 times. Nothing happens, you see. This is not printed, which means the signal is successfully blocked. Now I check. Is it really blocked? And I see, yes, it's pending for delivery. Now I unblock it and signal is delivered one time. So apparently Signals are not stored in a queue. Our experiment just confirmed that the signals seem to be merged into one when the same signal arrives multiple times. So you can send like 10 sig int, 5 sig user 1, 6 sig user 2. All of them will be delivered as just 1 sig int, 1 sig user 1, 1 sig user 2. But usually it's not an issue, like signal is not something you're supposed to use as a message of any way. It's just an event. You can multiple times say that certain event happened, but you don't need to. It's just enough to deliver it once, right? You don't need to repeat it many times. And in our case, we just have to manually deliver 3 more signals to exit the process. So the signal function, due to being almost unusable everywhere except for the simplest single-threaded programs, it needs an alternative, and that is how sig action function appeared, which is a system call on Linux. It's a very non-trivial function with huge power. The sig action function, it takes a signal ID to set an action for, a new action to install. What is the action we will obviously look at a bit later. Firstly, sig action function. So new handler and then again old fang handler. All those signal functions, you probably can already see a pattern that all of them are get and set. Again, this function is setting the new handler, returning the old handler, so you can restore it later if you want to the old value. Then what is sig action? It's a structure which has multiple members. First couple of members, it's a handler function. SA handler or SA sig action. Even though there are 2 functions, you actually are supposed to set only one of them, whichever you prefer. First one is looking exactly like the old one from the signal function. So it just takes an integer and that's it. And the second one is taking signal number as well and some additional information. If you need this additional information, you can choose to set this handler. It's going to be a bit more powerful, but it's very rare when you need such power, so probably most of the time you will be setting just the first one. The second one in siginfo will contain some very detailed information about the signal origins. For instance, if it was a segmentation fault, sigsegv signal, it will contain the fault address, which might be interesting actually, like, for instance, if you want to log the bad signal, it might be very helpful if the signal is actually null PTR, like 0. Then it will narrow down the crash reasons and will simplify your investigation later. But otherwise, I cannot honestly think of many cases when you could need this. And the last one is going to be something hardware and platform specific, some sort of context of the interrupted thread, which will contain, I guess, some registers and whatever else was saved when the thread was interrupted. This is very low level thing, which I honestly don't even know how to use. Maybe it is used for some sort of low level libraries. The next member is SA mask. It's a temporary mask to add to the thread signal mask during signal processing. So whichever signals you add to this mask, they will be blocked while the handler function is being executed. This is actually very convenient because this was not possible with signal function. With signal function, you could receive multiple signals recursively, and they would all be handled one on top of another without letting the previous one get finished first. It was not possible to block them, so to handle them one by one. With the sig action function, you can actually do that. Firstly, the signal itself, which you passed into sig action first argument, it will already be here by default. You don't need to specify it. By default, the signals coming to sig action handlers will always be handled one by one, never recursively. You can also block more signals if you want. You can fill this complete mask, for example, and then no other signals will be received by this thread while it is handling the current signal. And SA flags can regulate the behavior of the handler in some ways. For instance, you can choose SA no differs flag. Then it will behave like the old signal function. So it will allow you to receive the same signal recursively. Or say on stack. With this flag, you can choose to run your signal handler on a custom stack, not on the stack of your current thread, which can be very helpful. For example, if your stack is small and you want to place something big on the stack, or when you are handling, for instance, segmentation fault. Sometimes it can be caused by the stack being overflown, which means if you run signal handler on the same stack, it will not be able to run because the stack is already overflown and you are trying to place even more stuff on it. So the signal handler will crash again. It can be helpful sometimes to have a second stack just for signal handling for such cases. Or reset hand flag. It's also to simulate the behavior of the old signal function. It will make it so the handler is reset after first handling automatically. This is how signal is behaving, and you can technically simulate it here. Like a one-shot signal handling. It will not be handling signals repeatedly. And the last signal is, it's not the last, but the last one we are looking at. SI SIG-info signal. It's regulating which of the signal handlers to use. If you specify SI SIG-info flag, then this handler will be used by the kernel. If you do not specify this flag, then this handler will be used. To be honest, this looks very confusing because I would expect that I set one handler to null and another one to some non-null value, to a real function. Then the kernel would itself understand that the one which is null should not be used. Right? This would be simple, but for some reason it's not enough. You have to explicitly provide a flag which functions should be used. Let's consider an example where we try to use this advanced signal handler. I set it here for SIG-seg segmentation fault. I use the advanced handler using a SIG-info flag. As you can see, this function contains SIG-info argument and some context thing. And then I try to create a segmentation fault. I do it very simply by just dereferencing an invalid pointer. Obviously, pointer number 10 is invalid. I'm trying to assign something to it, and this will lead to a segmentation fault raised by the kernel. And then I can see what information is available here for the advanced handler. Let's see, so I am printing here the number of the signal 11. Yes, segmentation fault is technically 11, at least on Linux. And then SIG-info, it contains SIG number. Also 11, correct. The address, this is the fault address which caused the segmentation fault, which is 10, written in hexadecimal notation. And it was indeed 10. So we can find which address was problematic. And then the reason, you can also see the reason, like the address is just not mapped to physical memory. Yeah, it was true apparently. Or it can be access error. For instance, you tried to write into read-only memory. Or you tried to read memory which is protected, which is not available to you. You can see the reason in this SI code thing. The next example demonstrates how the signal mask is working. The program sets a handler for SIGUser1 here, as you can see, for SIGUser1. And this is the function on new signal, which will be checking if the user signal is blocked. Using my custom function isUser1 blocked. I will be checking if the signal is blocked during execution of the handler. And I will be checking it in two cases. Firstly, when I just created by default without this thing, or when I provide a command line argument no defer. When I do provide this argument, I will specify no defer flag, and then I will try to see how the behavior is changing. At the behavior, I will be checking using recursive signal delivery. So when signal comes, I print something, and then I try to raise it again. I will raise signal inside handler of that signal. If defer is enabled, then this raise will do nothing. The process will firstly finish the current signal, handling and then handle the next one. If no defer is enabled, then the signal will be instantly handled again recursively. And I will try to do it several times to see if I get the recursion or not. So let's try to run it. I compile it, I run it by default, so it's going to be blocked during handling. And then I see it is not blocked in the main function. Yes, this is what we would expect. Then we process the first signal. It is begin and end processing from beginning to the end. Raise was not handled right away. And then it is invoked second time to handle the raise. So the signal handler did not handle the second signal recursively, which is what we would expect from default behavior. And we can see that it was blocked during this time. And then when I specify the no defer flag, we can see that it becomes recursive. We begin handling of the first one, raise the signal, and instantly begin handling of the second one. Then we finish the second one, and then we finish the first one. So it was recursion, and the signal was not blocked anywhere. You see, it was always unblocked. It is also allowed technically to jump out of the signal handlers without returning from them gracefully. If you return from a signal gracefully, and the signal was handling some exceptional situation in the code, and you return from it, this code will be executed again. Signals, they are like exceptions in the hardware interrupts. So you can, when they happen, they get retried if you return from them gracefully. The instruction which was interrupted by them, it will be retried. Sometimes you don't want that. For instance, it's very unnatural scenario, but imagine you got a crash segmentation fault on attempt to dereference a bad address. If you just return from segmentation fault handler, then this instruction will try to get executed again, and you will get this signal again, and this will be a busy loop. The process will constantly receive signal, ignore it, receive signal, ignore it. This will raise your CPU usage to 100%, and then it will be very, very bad. And we also used this jumping out of the signal handler in the meltdown exploit on one of the previous lectures, if you remember. Let's try to do it here. When we know a bit more about signals, we can try to see how it's working. So I created here the jump buffer, which I'll use for saving context and jumping to it. I will jump to this context as soon as I get the signal, and the jumping will happen here back into the main function. So I will raise the signal and then jump back here, right out of the signal handler. The sequence will be like this. I go here, I raise the signal, I go here, and jump will throw me here. And then I continue execution like nothing happened. Let's see how it's working. Somehow it works different on Mac and on Linux. Let's see. On Linux, before raising the signal, I see that the sig user 1 was blocked. Then I processed the signal. During processing, it was blocked, obviously, by default, because I did not specify no defer flag. Then after raise, I jump into the main function, and user signal remains blocked. I exited the signal handler, but the signal is still blocked. So I broke something. Apparently it's not supposed to happen. I was expecting that as soon as I leave signal handler, the signal mask is going to be restored back, and it was not restored back. On Mac it was, for some reason. We don't know yet why it happened, but here it behaved like I expected. It was unblocked in the main, was blocked during handling, is again unblocked in the main function. So what is really happening here? The problem is that the jump buff, the normal one, it contains the context by which you can like jump back to a specific place on the stack and continue executing specific instructions from a certain point. So it's a context which you can save and then you can restore. And the thing is that on Linux, this context, it does not include the process, the signal mask of the thread. Just doesn't include it. It's not considered part of the context. And on Mac it does. So on Mac, when I was doing set jump, long jump, set jump was saving the current signal mask of the thread, and long jump was restoring it using sigprots mask. And on Linux it just wasn't happening. Probably because it's not required by the standard, and sigprots mask is a system call which is expensive to invoke, and this makes set jump and long jump relatively expensive on Mac. And so on Linux it wasn't done because it wasn't required by the standard. And apparently at some point it became needed, so it should work. And I don't know why somebody couldn't just implement it on top of long jumps. But for some reason they decided to add it to the standard library, and now we also have parallel implementation of those jumps called sig jump buff, sig long jump, sig set jump. And they do all the same as what the normal jumps are doing, but also they preserve the thread signal mask. And then it works identical on Mac and on Linux. So if we run it, we see that now on Linux it's also restored because the signal mask is part of the context here. These features solve all the problems of signal function except for one last. How to set a signal handler and wait for the signal receipt atomically, preventing the signal from coming between these two actions. If it would come after you set the handler, but before you call something like pause, then the thread will be blocked. We saw it in the very beginning of considering how signal function is working. For doing it properly, there is a function sigsuspend. It takes a signal mask and atomically sets it plus calls pause. And after returning from the function, the old mask will be restored back. And this is all happening inside. We don't need to think about it and handle it manually in our code, which can be very convenient. So this is a temporary mask. It's wait signal width. Let's consider an example. Here we want to count how many times sig int was received. Similar to our old example some slides ago with normal signal function. The main function wants to wait for at least one sig int and then exit. To perform this simple task, we will use sig action, sig prots mask, and sig suspend combined together. At the beginning of this example, I start by blocking sig int. It's a good idea to do always when you want to start doing some shady business with signals. You just first block them, so they don't come in the middle of you trying to change how they are being handled. This would be dangerous if they come in the middle of you doing some work on them. So we block sig int firstly. Next I set the signal handler using sig action. It will do what? It will increment our finished counter on which the main function will be waiting. And then I call sig suspend. This invocation of sig suspend will make so it will atomically set the empty signal mask into the current thread, so all signals get unblocked, and it calls pause. In this way I can wait safely until my signal is received. If this would be not one action but two actions, then this would deadlock, as we have seen it previously. But sig suspend is doing it for us atomically. Internally, sig suspend obviously is going to be probably multiple actions, but they are organized in a way that it's identical like if this would be done atomically as a single action. Let's run it. So we see before main the sig int is unblocked, then I press Ctrl C, it is received, it is blocked during receipt, then I exit the main. So no matter how you do it, this program will not deadlock. Signal handlers run on the same stack as the interrupted thread, but this can be changed technically. For example, as I mentioned before, if you either want to use a lot of space on the stack, for example, to avoid heap, you can just create a large memory block on the stack and use it for allocating things instead of the heap to avoid heap usage, right? Because heap is unsafe to use during signal handling. Or alternatively, you might want to cover the case when your thread crashed, received signal because of stack overflow. Then you obviously cannot use this stack anymore, right? On the default stack, you might be just unable to handle stack overflow at all. This would be inconvenient. So for this case, when you want a separate, bigger stack probably, or just stack which is guaranteed not to be affected by whatever is broken in the main thread, you can use sig alt stack function. It allows you to set or get again, like the logic is get and set. So it will allows you to set a new custom stack and receive the old stack, whatever it was. And the stack itself is what you probably would expect. It's a pointer at the stack and its size. Some flags, they actually regulate not the stack itself, but how to apply this stack. Like what to do with the stack. They don't regulate any attributes of the stack memory itself. So it's a new stack, and the old stack you can get as an output parameter if you want, but you can also give it as null, and then you don't get anything. As a stack size, it might be challenging to choose the perfect stack size for your use case. You have to kind of think, try to estimate how much memory you are going to use on this signal stack. But also there can be some helpful constants in the standard library, like sig stack size constant advised size, whatever it means. You would have to print it to see what it's equal on your system, and mean sig stack size, minimal possible size. But again, I honestly don't know which guarantees they give. Normally, how I would do it, I would choose some constant of my choice, like 1 megabyte or 16 megabytes, I don't know, and take maximal value between my value and this one. So it's at least advised, but most likely will be even bigger, and then I will have more freedom to what to do with this stack. And the flag, the only really flag that matters is SS disable. So when you, with sig alt stack, provide a new stack, it will be set for the current thread. And all the signals coming to this thread will be handled on this stack if they were chosen to in the sig action function. But how do you remove the stack? Like imagine you set a stack for the current thread for signals, and then you don't want it anymore. You want to take it out and then free the memory when the process is being terminated gracefully. Right? How do you take it out? Do you set an empty stack or what? So instead, what is supposed to happen, a bit counterintuitive, but it is what it is. You're supposed to give as an input parameter a stack T object which has SS disable flag. Other members don't even matter. As soon as you specify SS disable, other members are ignored anyway. So you specify this disable thing, and then this thread will no longer use this stack for signal handling. And then you can free its memory, because you probably allocated it on the heap and you want to free it eventually. Let's see an example. So in this example, I run the same signal handler in two ways. By default on the interrupted threads stack and on a custom newly created stack set with sig alt stack function. And the handler will then print some addresses from the stack, so I could compare it with the custom stack address and with the main stack address and see where is actually my stack, which stack is used for the handler. So firstly, I need to create my custom stack. It might be a little bit untrivial to do, to be honest, because not only your stack should be big enough, but also ideally it should be aligned by the page size, because anyway, the memory is managed by pages, and you need at least one page to be turned into a stack by the kernel. It's not so easy. It's not like not any memory you can use for stack. The memory which you will be give to the kernel, it will pre-process it a little bit to set some certain like attributes, whether this should be executable, read-write, read-only, or whatever. So it will operate on the pages anyway. So you can as well just allocate in pages, not in just bytes. And here I get the current page size of the system. I rounded up the size that I gave to the page size, so it's multiple of page size. I choose at least the advised stack size, and then I allocate it using simple malloc. Where do you get this memory from doesn't matter. It could be malloc, it could be a global array of char, it could be stack of your even current thread. You can use part of the stack as a stack, technically, if you want. Doesn't matter, you just have to take this memory from somewhere. In this case, I just allocated it on the heap. I set its size and I call cgalt stack with this provided stack. So now it is set for my thread as a special stack for signal handling. And when I will want to delete the stack, I have stack destroy function, which will get the current stack. So the new one is null and the old one is output specified parameter. I specify disable. I call it again. To disable it explicitly, I have to do it before freeing the memory. Then I can finally free it. Now in the main function, we will firstly try to run a handler on the custom stack. The stack is installed. I call this stack create thing. It will be 64 kilobytes in my case. And then I install a signal handler for SigUser1, which will be running on custom stack. For that, I have to specify SA on stack. If I do not specify this flag, the signal will still be handled on on the stack of my thread. I do not want this, so I have to specify this flag. And I have to provide the custom stack, and then it will work as I expect. So then I will wait for signal to come, and then I will remove the stack. And then I will try it again without the custom stack. As you can see, I removed this flag and the stack is destroyed. So this is how it would work by default. And this is how it works when I provide custom stack. Let's run it. So the main stack, it has approximately this address or something, like at least it contains this address, because I printed some variable from this stack of my thread. Then we run the handler on the first signal on the custom stack. And we can see my custom stack has this range of addresses, and inside the handler, the address of some variable on the stack was this. So it's clearly between those values. My custom stack was indeed used. This one is very far from the thread stack. It is definitely not my thread stack, which is good. This is what I expected. You see? And then second time when I call it without the custom stack, I can see that the value is very different now. The stack of the signal handler is very close to the main thread stack. It's basically main thread stack, not my custom one anymore. So what those signals can be typically used for? I would say it's only really three things from what I have seen. First one is obviously crash handling. When on a crash signal like SigSeg, you want to print something into the logs, collect whatever data you want, dump it somewhere on disk, and then the process is terminated, and then you can use this information later for debugging. Another case is graceful termination. It's when your process is running in the background and you want eventually to terminate it. Then you can send it a signal like sigterm, and your process in advance already installed the handler for sigterm, and the reaction in this handler is to gracefully terminate everything. Free all the memory, flush all the logs, gracefully close all the sockets, and so on. This is probably even more frequent than crashes. And the last one maybe is things like log rotation. For instance, your application is writing logs into a file, and then when the file gets really big, you want to start writing it to a new file, and the previous one would be eventually deleted or archived or whatever, right? This is called log rotation. And it can be done in applications by timeout and or at the same time by signal. So if you're If your application is a bit advanced in the logging, then you can set a signal handler for, let's say, sig user 1 or for sig hub, I don't know. And in the handler, you can close the old log file, create a new log file, and then your logging is writing into a fresh file. This is 3 typical use cases I can think of right away. But you can also use signals for some untrivial and interesting and counterintuitive things for which you probably would never think they can be used for. In our case, I found a way how to use signals for implementing C coroutines, using only C code without any assembly lines, which are often used in the coroutine implementation and C and C++, stackful coroutines, I mean. And before we do this, we need a plan how to do it. An initial naive idea which I had, it wasn't even involving signals at all, was to make stackless coroutines, like in C++, those resumable functions. And those C coroutines would work all on one stack, and they would use long jumps for switching. The problem is that they would be sharing one stack, and this would be very bad, but I thought it could be worked around it anyway, because I would just give every coroutine a huge struct where they would store all the local variables, and then it would work somehow. However, there is a fundamental problem with such approach, which is that setJump does not survive return from any function. There are ways how to work this around. You can create custom context in a struct located on the heap. Don't use stack at all. You can avoid returns. Always use jump instead of return. But this will be looking very, very ugly. Believe me, I tried. The point is that this case is interesting in a sense in order to understand how stack is working really. Let's see an example. There is a following extremely simple program which calls a function testf, which calls another function testf2, which does setJump, increments some sort of counter, and then returns back, and then returns back, and then returns back into the main function. This seems okay, right? In the main function, then it will print that first call was okay, and then it does long jump back. So first call, it was used to climb up the stack, and then we jump back on top of the stack, bypassing all the function calls. Bypassing this, and this, and this, we just jump directly into this place of the code. And we expect this to work, so we would expect that it returns, and then returns again, and then it's back here. The problem is that it doesn't work. This code will crash almost 100%, or will make some sort of undefined crazy behavior, but on my machine it was crashing. I run it and it crashes. Even though technically, logically it looks correct, right? This is, I was expecting at least myself that setJump and long jump would be working. I suggest you to think about why did it happen. This might be slightly untrivial, but try to think. What was happening here that first call worked okay, and then after jump it broke. I will firstly give you a hint. If you don't want a hint, put on pause. If you want a hint, continue listening. Hint is that after our jump, this will work okay. This line will work okay. This line will work okay. This one will crash. Try to think. If you want to know the answer, to check, or just you didn't even try and you just scroll to the answer, I will reveal it right now. The problem is that yes, I wrote it, revealed on the lecture, because I will explain it verbally. The point is that the stack is used not only for function arguments and for local variables. It is also used for some hidden implicit things which you do not see. One of which is return address. When you call return in any function where it's implicit, like even when you don't call it, here is actually return added by the compiler. You don't have to call it explicitly, right? Return, what it is doing. It needs to know where to return to. Where to return to is stored on the stack as the return address. Return is basically a go-to. It will go to the address of the calling function, which means this address should be on the stack. And when it is placed on the stack, it is placed when you call the function. When you call a function, return address is placed on the stack before the call. If you did not call the function, if you just entered it by jumping directly into it, then you have no return address. An attempt to use it will lead to undefined behavior. Let's see what was happening in this example. So main function, it is started. Now we try to call testf function. We enter it. We call testf function. The stack currently contains return address to main. I call testf2. I enter it. Stack now contains return to testf. Now I remember the current position on the stack and the current instruction, and I return. Return is go to this latest address on the stack. So I use it and for jumping here. Here I also immediately do return to the main. I use this address as go to. I am jumping. Then those addresses technically are still on the stack. They did not get deleted or anything. But now I do the following. I call printf. Printf is a relatively untrivial function which will use the stack for whatever, for some internal things. I don't know what it's doing. It will basically override the stack with some trash, which makes no sense for my own code at all. Not return addresses, but some sort of invalid values. And then I make long jump into testf2. I try to return. I try to take return address. But there is nothing. There is probably something, but it's probably trash. And I try to go to by this address. It's probably not even an instruction address. And then I simply crash. This is what is happening here. There is still a way how to make it work. How to make stackless coroutines work on a single stack with long jumps, but implementation would be very ugly. It would be very interesting and curious to do, but it will be looking very bad. Like not even C language at all. Because you would be unable to use return, you would be unable to use local variables on the stack. You would always allocate all the contexts on the heap. This will not look good. You could, like, return problem you could bypass by having your own stack of return addresses allocated on the heap for every coroutine as an array. Like stack data structure, I mean literally inside each coroutine. And when you call a function, your current coroutine will have to save the return address using setJump, and instead of return you will have to call your custom coro return or whatever, which will take the latest jump buff from your stack of the coroutine, custom stack, and make long jump on it. So you will be unable not even just to return, but even calling functions will have to be wrapped into special macroses or functions or whatever you do there. But it will work. You can make it work technically. I did try, it was working. It was looking very bad. We can still use long jumps, and we can still find a way to do return and use local variables and all this, but we need an alternative way. The stackless coroutines have very narrow usage, I would say. It's not very convenient to use most of the time, even when all the local variables and returns and all the other stuff is allowed, like in C++. The stackless coroutines come out of the box, but it's very hard to use them for anything untrivial. Because of multiple reasons, including the ones which I just listed about local variables, return addresses, all this stuff. Those things are not problem when you have your own stack in every coroutine, and coroutine can just store it there normally, like you would do in regular code. And technically, we can do this using signals. What we can try to do is, what we need to do first. We need to do the following. We need to create a custom stack on which a coroutine would be able to run. And we need to be able to jump on this stack. Where can we get the custom stack from? The sig_alt_stack function technically can help us to create a custom usable stack. Then we can send a signal to ourselves, and this will make the kernel bring us to the top of our stack, custom stack. And then we can remember this position with setJump, and then we can jump back into the code which created this coroutine, And then what we have is a coroutine stack saved in some sort of struct, coro or whatever. And we have a jump boof which is pointing to the top of that stack. So we can any moment jump there and execute something on that stack and then jump back. So we have a second usable stack in our thread, and we can create many of them, and each of them can technically be running its own code, which means we essentially invented stackful coroutines. And then on top of that, we start facing some other issues like how do you define which coroutine should switch to the which next coroutine and at which moments, and how do you handle them being blocked on things, how do you handle some sort of mutexes, which would be potentially used inside one thread by different coroutines and so on. So on top of that, you can build the whole ecosystem and runtime and end up with things as complicated as like just green threads in a single thread. You run many coroutines with your custom simple synchronization primitives, or even multi-threaded coroutine ecosystem like goroutines in Go language. I tried to actually implement something like this in a library libcoro, which you also had the chance to use in the first homework. And it is completely based on this signaling idea. I will not dive into implementation details too much. You can look up the code yourself. It's completely available. It is using everything what we have learned on the lectures so far. Then once you get into this black hole of implementing your own runtime, your own coroutines, your own synchronization primitives, the coroutines by design are cooperative multitasking, which means your coroutines will have to voluntarily give control away to some other coroutines of their choice. This works well and the context is small in size, like for instance one process code of which you completely control, and you know the specifics when is the good time to switch one coroutine to another. You can control how they get synchronized, whether they run on one thread, on multiple threads, whether should they do blocking IO or they should do asynchronous IO and switch to other coroutines to wait for the IO to get completed, if some coroutines should be doing just IO and others are not, right? So you can build a working fair ecosystem of coroutines when you control it completely. And still, even then, you might be having sometimes issues like one coroutine due to a bug or wrong settings of some sort of your application might be running too long without giving control to the other coroutines. And then the other coroutines will be starving, because if your coroutine it doesn't give them control, then they will not be running, right? They will not be doing work. This problem does not exist in the kernel and the threads, which is scheduled by the kernel, because kernel is using different multitasking way. It is using preemptive multitasking, not cooperative. This problem doesn't exist in the large scale of the whole system, because the system will interrupt the threads when the system wants that, when the system considers it fair. Unlike with cooperative multitasking, when you have to organize it yourself manually. And while cooperative can be, when done properly, very, very fast and beneficial for performance and easy to manage, the preemptive multitasking technically is safer and easier to scale. And this is bringing us to an interesting large topic, whether it is possible to implement preemptive scheduler in user space for coroutines. Using those signals hack, for example, it could be one way. Yeah, this, to be honest, this is the only way I can think of personally. Is that we could have some threads running many coroutines in them, and we could have a separate thread which is doing scheduling. So it remembers all the coroutines and all the threads, which one is running for how long, and then it could be waiting for certain timeout, like 1 millisecond maximum, and then it will forcefully switch coroutines in those threads to different ones by sending those threads targeted signals, targeted to specific threads. And the threads will interrupt their current coroutine, and the signal handler will see that they exceeded the time slice, and will switch the coroutine to another one. This is something which is technically absolutely possible. The only problem is that we will get in conflict with the standard library, because the standard library is not suitable for such usage when you on purpose send signals frequently enough while you are, for example, doing malloc inside a certain coroutine. You will get this case much more frequently, which means you either cannot use heap at all in your whole application, which makes no sense, or you would have to implement your own heap, which would be signal safe. So this probably, I think, is what's done in Go language with the Go routines, as far as I know at least. Can also be done manually if you want to try some experiments to learn. This is a perfect opportunity to learn how it's all working, because you will have to implement everything from scratch, whole runtime of almost basically a new language. And there you will learn about multi-threading, about signals, about heap, about synchronization. Like you will also have to build your own custom mutexes, which should be working for same coroutines inside one thread, which is not normal mutexes what are for, right? This I did not try to implement, but I can imagine it could be a very interesting side project for somebody who would want to dive into this topic even deeper. Let's summarize what we have learned today. Firstly, interrupts can be of two types: software for exceptions on the CPU, and hardware for handling events from devices, like disks, RAM, time sources, and so on. Signals are similar to interrupts, but for processes. They are raised by the kernel on certain events, or they can be raised by the processes on their own and be sent to other processes. Most of the signals you can intercept and process, besides two signals, seek kill and seek stop. They are not interruptible or blockable or anything. Seek action is new and good. Signal function is old and bad. You should not be using it. It's broken. If you are using it, stop doing so. Either use sig action or use some sort of wrapper on top of those functions, like from Boost and C++. It has pretty decent signal handling API. And both those functions allow you to control signal handling per process. Signal handler is always process-wide thing. It is not possible to set different signal handlers for different threads. Signal handler per whole process. Signal mask is for every thread. Most of the signals you can block or ignore by threads of your choice via sigproc mask. If you block a signal and then you unblock it and it was delivered while it was blocked, then it will instantly be processed. And multiple signals delivered while blocked will be merged into one. Signals of the same type at least. You can use your own stack for signal handling and do some funny stuff with it, like create your own coroutines using signals. Signal handler is a very dangerous place where it is not safe to do almost anything. And the list of safe to use standard functions you can find in MAN7 signal, or you can Google signal safe functions and use a link like on the slide to see the list. Next time we will be dealing with file systems. Again, starting from the disk, into the kernel, into the user space, we will see what is a virtual file system, how are files stored and organized, what are their types. We will see I/O operations in the kernel, I/O schedulers, page cache, how HDD and SSD are working, and honestly many other things. The next lecture is quite rich on the content, I would say. Thank you for listening and see you next time.